This is Lesson 10A, Unit 11. We're going to look at titrating a weak base with a strong acid. This is an introduction with looking at the curve. So we're titrating an amine with a strong acid to make an ammonium salt. Okay, so here's an example of 40 mLs of some amine titrated with 0.12 molar hydrochloric acid. We're going to determine the concentration of the amine using the titration curve, and the way we would do that is to find the equivalence point. This is when our moles of amine equal the moles of the hydrogen ion, and we use the equation MAVA equals MBVB. The amine is in our flask, the hydrochloric acid is in the burette. So let's start off with just characterizing the major species present at various points along the titration. At 0 mLs, we have not yet started adding any hydrogen ion, so we have only RNH2. And we're going to end up using an ICE table for that. At 50 mLs, we're in the steepest part of the curve. We're at the equivalence point. At this point, these two reactants have completely consumed each other, equal molar quantities, and we have only the ammonium salt left. Now this is going to set up an equilibrium, so we are going to end up using an ICE table here, as you will see. So I'm going to go ahead and write ICE here. In between, we have what is called the half equivalence point. So this is at 25 mLs, so we have the 1/2 equivalence point. And just like the weak acid titrated with a strong base, we're going to have the same setup where we've made a buffer where we have equal amounts of RNH2 and RNH3. So what we have is that RNH2 concentration is equal to the RNH3 concentration at this point right here. We can just go through the logic. If we have only the amine here and half here at 10 mLs in between, we must have significant quantities of both, but we have more of the RNH2. So we have RNH2 is in greater concentration than the RNH3 plus. Once we're past 25 mLs, so in this case it's saying 40, we're still making buffer. We still have both species present, but now we have less of the RNH2 than we do of the ammonium salt. So we keep going. We get to the equivalence point where we can use MAVA equals MBVP. Once we get past this point, this means that we have excess hydrogen ion. So we still have RNH3 present. We've made all of that we are going to make, and then we have excess hydrogen ion, and this will just keep increasing in concentration the more we get past this endpoint here. At this point, the excess hydrogen ion is going to control the pH. So just like with the weak acid titration, we've got a buffer region where I'm drawing it in with the blue, where the pH does not change very much. I'll get fancy here and color it in. So this is our buffer region. And when we go to do our calculations, we're going to be able to use that equation pH equals pKa plus log A minus over HA. Okay, so we're going to summarize the features of a weak base being titrated with a strong acid from the previous curve. Our initial pH is going to be greater than 7 because we're starting with a base. The initial hydroxide concentration is lower than the initial concentration of weak base. This is because only a portion of the weak base ionizes. So what this means is if we have something like RNH2, if it's 0.1 molar, there's much less of the OH minus because we're going to be setting up an equilibrium. So we can't use this initial pH here to calculate the concentration of RNH2. We're going to have to use an ICE table there to calculate the pH. The pH decreases rapidly for the first 5% of the titration. So if we go up here, we see there's a sharp drop off in the pH to start off with. The pH decreases slowly in the buffer region before the equivalence point because we have substantial amounts of both species present. At the half equivalency points, 25 mLs in this case, we can figure out the pKa. So at this point, pH is equal to pKa, but if we're asked for the pKb, we have to remember to convert to the pKb. So the pH will give us the pKa. Remember, if you're asked for the pKb, you need to go through the conversion. The equivalence point is going to be less than 7, and let's take a look at why that is. We have gone through this reaction where we have equal molar amounts, so it's going to be a 1-to-1 ratio here. At this point, we're setting up the equilibrium with the ammonium salt with water. We're going to be making small amounts of H3O+. We're going to be using an ice table to figure this out, and so the pH is going to be less than 7. Anytime we have a pH titration curve, we can use the mLs at the equivalence point to solve for the unknown concentration. And so I have that shown here. Let me bring this up just a little bit. So solving the concentration problem from the above problem, we had 50 mLs of the H+, our molarity is 0.12 molar. We had 40 mLs of the original RNH2. We didn't know the molarity. We simply set up MAVA equals MBVB, and we can calculate the molarity of the base.